Okay, is that all right? Can you see that all right? Okay, brilliant. Well, thank you very much for inviting me to give this talk, and I've really enjoyed the series so far, and so I'm really happy to be involved. And so today I'm going to talk about a really specific application of fluorescent nanodiamonds, hopefully also a topical application, which are fluorescent nanodiamonds for rapid, sensitive, low-cost diagnostics. So yeah, just a little bit on my background. Yeah, as Olga said, I did my undergrad and master's in electrical and electronic engineering, and yeah, my first experience was impedance-based sensing, and I just dug this picture out from my master's thesis. And then I moved to UCL and started my PhD in the McKendry group as part of the iSense consortium, which I'll talk about a little bit in a minute, mostly focusing on lateral flow tests and improving sensitivity and looking at the kind of the binding that happens in lateral flow tests and looking at the nanoparticles, and yeah, specifically focusing on optical nanoparticles. And now I'm a postdoc at UCL, focusing on the same sorts of things. So just to start, I just wanted to explain a little bit about what iSense does. So this is our interdisciplinary research collaboration between 5 UK universities in agile early warning sensing systems for infectious diseases and antimicrobial resistance. And the tagline is harnessing the power of mobile phones, nanotechnology, genomics, and big data to prevent infections. And there are 3 main branches of this. And I'll do the first one, then I'll go left, right, and then middle. So track is about using Twitter and Google search data to predict and nowcast infectious disease outbreaks. And actually, some of the algorithms developed as part of that branch have been adopted by Public Health England for and used in their online COVID surveillance reports, which is really exciting. And then on the right, and the treat side of things, that's about kind of taking all this data and presenting it in ways that are useful to decision makers. And then in the middle this is the bit that I work on. So this is the test, which is about developing rapid, low-cost infectious disease diagnostics. This is just my other slide about iSense. Just looking at the kind of the workflow and the different, it's a very interdisciplinary project, so the different areas that go into our work. So we start at the top with end user needs to make sure that the stuff we're doing is useful, hopefully. And then we look at biomarker discovery and capture ligands, which is the first step of any sort of diagnostic effort. And then this is more kind of my kind of area, looking at nanomaterials and nanosensors sensing. And then, as I talked about, the big data analytics and apps and dashboard form the other 2 areas. Actually, maybe I can, yeah. So what I mostly work on is lateral flow tests, and that's what is going to be the basis of what I'm going to talk about today. So why do I really like lateral flow tests is because they're rapid, because they're easy to use. You can do multi-step assays with very little user input, thanks to the capillary flow which is a property of nitrocellulose paper. They often have a colorimetric readout, so they can be read by eye, which again is nice and simple and equipment free. And pregnancy tests are a really good example of that. And then the negative is sensitivity. So although the sensitivity is still good and sufficient for lots of applications, like as pregnancy testing or HIV antibody testing is a very common application of lateral flow tests, the sensitivity is not suitable for detecting very low levels of biomarkers, which is often necessary for early detection of infectious diseases, which is what we're really focused on. So I'm just going to really quickly run through how lateral flow tests work. And explaining this has become a much less important part of talks since in the past year, certainly every news program or UK government briefing that I've seen has had at least one description of how lateral flow tests work. So on the left is a kind of schematic version of how lateral flow tests work. So you have your analyte, your sample gets dropped on the end of the strip, which contains your analyte of interest. And then by capillary action, so power-free, the analyte will start to spread along the strip where it encounters the conjugate pad, where you have these usually gold nanoparticle conjugates. So gold nanoparticles with antibodies on them that are specific to the analyte of interest. So if the analyte's there, they'll bind into these nanoparticle antibody analyte complexes and carry on running down the strip, where they come to the test line. And the test line usually has antibodies immobilized, which recognize ideally a different paratope of the same antigen. So you end up binding in this kind of sandwich structure. So sort of an antibody sandwich with the analyte as the filling. And so you immobilize gold nanoparticles in that way. And so if there's no analyte, these antibodies will not stick at the test line. And then the control line is just to say that the test has run all the way to the end. And just for further explanation, I borrowed this video from Abingdon Health, which is a very nice video. So usually the tests have this cassette, but the real test itself is just this bit of paper. This is a multiplex test, which has 2 test lines, which will detect 2 different analytes usually. This bit's slightly confusing. It kind of looks like you're mixing all these different bodily fluids together, but that's obviously not what would really happen. You would pick one, and that would form the basis of the test. And yeah, as I said, it gets absorbed onto the strip and travels up by capillary action with the analyte of interest, binds to these gold nanoparticle conjugates. And here they've got, for the test line, they've got gold nanoparticles with these kind of purple and black things on. I'm not sure what they are. But yeah, again, that's just to say that the test has run all the way to the end. And there's 2 different sandwich bindings happening there. Yeah, anyway, that's that. And then you have this sample pad at the end to kind of absorb the fluid and absorb the excess sample and the excess nanoparticles. So, okay, you should be able to skip ahead now. Okay. So just to summarize, sensitivity is what I've been working on. And this has been really highlighted, the need for sensitivity has been really highlighted by the COVID-19 pandemic. So there are currently over 400 RDTs, rapid diagnostic tests, which are used here as a synonym for lateral flow tests, in the FIND pipeline, which is the Foundation for Innovative Diagnostics. In the UK, in Liverpool, there was a pilot study where they showed that 60%, this was a pilot study testing asymptomatic people for COVID-19 using lateral flow tests, and they showed that 60% of infected symptomless people went undetected. Although this is, so there is a relationship between, so higher viral loads are more likely to be detected, which is good, but it's still, the study showed that they still missed 33% in the top 2 highest viral load bands, which is where you seem to have the highest risk of infection, of transmission, I mean. And then along with this, this study showing that a quarter of infections are asymptomatic, that really underlines the need for these, for rapid tests that are sensitive to detect these asymptomatic carriers and reduce onward transmission. So what are the factors that limit sensitivity? So, well, as of 2010, 75% of lateral flow assays used colloidal gold nanoparticle labels. So this is a little bit out of date, but still the vast majority use gold nanoparticle labels. And gold nanoparticles are great because they can be sort of easily manufactured in all these different, well, really flexibly. They can be functionalized easily. And they give this nice, the red line, which people are probably used to seeing. And the factors that limit sensitivity are the particle size and particle aspect ratio. So the larger the particle, the more light it will absorb. So the more light absorption per particle there'll be, and that correlates to the more light absorption per analyte in the sample. But there's unfortunately an upper limit. You can't just keep increasing the size of the gold nanoparticles, because past a certain point, the plasmonic peak starts broadening out. And they become not very useful. And then your sensitivity is also limited. Your analytical sensitivity I'm talking about is also limited by the resolution of your sensor, the ability of the sensor to distinguish between no nanoparticles bound and a few nanoparticles bound. Other than that, there are various biophysical factors that affect sensitivity, so especially the binding rates of the various components of the test. So this is a figure from a really nice computational modeling paper where they looked at modeling the different factors that contribute towards sensitivity, and these are kind of all the 6 different binding reactions they considered. Non-specific binding is a major challenge, so nanoparticles binding in the absence of the analyte, increasing the blank signal, and so reducing your sensitivity. Nanoparticle concentration is obviously related to those other 2 factors, especially the binding rate. And the sample volume, flow rate, all of that can affect sensitivity as well. And this was a nice graphic from the same paper looking at the factor improvement of adjusting these various different parameters. And so this is really interesting, but you can see that these improvement factors are still pretty small. So you need a really big increase in the binding rate of your antibody, for example, to get a big improvement in sensitivity from this side of things. So that's why we focused on the nanoparticle side to try and sort of like the top-down approach to try and improve sensitivity that way by improving the signal per bound particle and the signal per analyte. So there are various ways that people have tried to do this kind of thing with gold nanoparticles, just to give you a bit of background. This is a paper where they used a secondary antibody to bind multiple gold nanoparticles per analyte to improve the signal that way. And this is a paper constructing gold nanoparticles into these chain structures to bind multiple per analyte. And this is following the same kind of approach, so using DNA to generate these nanoparticle structures, which were then bound to the test line. So in this picture, for example, you have 5 nanoparticles bind for each analyte, or for each strand of DNA in this case. This is a slightly different approach, using thermal imaging instead of conventional green light absorption. And I think they got about a 10-fold factor improvement in sensitivity. And then, of course, people have also tried to use different nanoparticles. So this is another paper from iSense where platinum nanocatalysts were used, and that allowed the catalytic enhancement using an enzyme substrate to improve the sensitivity 100-fold. So those are kind of approaches relying on absorption-based signals, but we're looking at fluorescence-based signals. So this is an example of a fluorescence-based lateral flow test using quantum dots, actually. And the key thing about this paper actually is this figure on the right here, where they measured the quantum dots are really good for make a fluorescent test line, which can be really sensitive. The problem is that the nitrocellulose membrane, the substrate of the test, also has pretty high autofluorescence. So these bottom 4 images here are 4 different membranes, and you can see that, and these are the excitation and emission spaces. And so you can see that there's quite a lot of background fluorescence, especially for quantum dots, you'd want to be exciting in this kind of range. And here there's quite a lot of background fluorescence, which will obscure low signals. And here, for comparison, there's a 50 nanomolar solution of quantum dots, which is quite a lot of quantum dots, showing kind of similar magnitude responses to this membrane, for example. So this is the real problem with using fluorescent nanoparticles on lateral flow tests. They can be really sensitive, but they're limited by this background autofluorescence. Another example actually of quantum dot lateral flow tests, a commercial example, was from Ellume Health, which actually just a few days ago in the news, I think the US government has bought $230 million of quantum dot based lateral flow tests from them. So these fluorescent nanoparticle lateral flow tests are seeing some real applications. These are COVID tests, and what was really elegant about this is they have all the optics required for fluorescence measurements built into the test cassette itself, which is really nice. People have used europium microparticles, and then these upconverting phosphors, which is a kind of approach to get around this background autofluorescence problem as well, by exciting in the near infrared range where the autofluorescence of the membrane is lower. The same with long persistent fluorophores, so you can use time-gated fluorescence to try and remove that background fluorescence. And then a slightly different approach that's been used is trying to reduce the autofluorescence of the membrane itself rather than changing the particles. So, bearing that in mind, we wanted to focus on the nanoparticle side, and so we were looking at using fluorescent nanodiamonds containing nitrogen vacancy centers as our fluorescent label. So this is a TEM of an SEM, sorry, of some particles from Adamas, and here is a diagram that has been in most of the talks, I think, which is the NV center. So you have in the carbon lattice, you have a substitutional nitrogen atom and an adjacent vacancy, and that makes the electronic structure, which is the origin of the fluorescence. And I'm not a quantum physicist, but I'll do my best explanation that I have using this energy diagram. So what you have is you have your triplet ground state and triplet excited state, and the electrons can be excited by green light, peak around 550 nanometers, into the excited states. So the ms equals 0 and ms equals ±1 are excited into the excited state, and then can decay back into the ground state and emit a photon, spin being conserved. But there's also this alternative route via this singlet dark state, where the electrons can go from this ms equals ±1 excited state chicken salad with the chili. down into the ground state via this singlet dark state, where no photon is emitted and spin is not conserved. And so what that means is that by applying a microwave or magnetic field with the size either delta E or delta E star, you can push or pump these electrons from the ms equals 0 into the ms equals ±1 states. So you can increase the number of electrons that will decay via this dark state, and therefore reduce the fluorescence. So we did some measurements of this. This was actually a measurement done on paper on a lateral flow test. So we did a big sweep of microwave frequency, and we looked at the fluorescence. And so you can see a dip in fluorescence at this delta E star, and then another dip at the 2.87 gigahertz delta E, which is the ground state splitting. And we use this 2.87 gigahertz frequency for all of our work. The way that we coupled those microwaves is we used we used two different resonators. So these are antenna resonators attached to a voltage controlled oscillator and through an amplifier. And so for wideband measurements like this, we use this linear resonator, which has quite a broad frequency, a broad kind of flattish frequency response. And then for the rest of our work, where we just wanted to have the maximum possible signal at 2.87 gigahertz, we used this omega resonator. And so the idea was to have a sort of high uniform field in the middle of the resonator in this area that we were going to image. And this is an overlay of the power absorption of the antenna resonator, and then this is a fluorescent signal overlaid on top of it. And then finally up here you can see as you increase the microwave generator power, you see a decrease in the fluorescence, and integrating these lines and then plotting against microwave power, you can see this kind of linear decrease in terms of power in decibels, so a power relationship. So this is an illustration of what we did. So it's very similar to the lateral flow test before. It's a sandwich assay, so we have a capture molecule printed on the strip, mobilized on the strip, and then you have antibodies on these fluorescent nanodiamonds. And then they're binding in a sandwich structure, but just instead of the analyte in this case is double-stranded DNA with two small molecule modifications, which are biotin and digoxygenin. And then we have our omega resonator here generating the microwave field. This is a more sort of schematic look at the whole thing, but it's showing the same thing really. And yeah, just if you can see a bit more clearly the sandwich structure here. So these are the two capture molecules, and then this is the analyte. So what we did actually is we applied the microwave. So we took inspiration from a couple of papers actually that have been using nanodiamonds for in vivo imaging, and we applied the same kind of principles. So we used an amplitude modulated microwave frequency electromagnetic field, and so we were able to reduce and then increase again the fluorescence at a set frequency. And that's what that looks like. This is the test line of I don't know if you can actually see that. It's kind of pulsing, but this is the test line of a lateral flow strip. It's a close up, and the test line's running in that direction, up and down. And you can see it kind of flashing. And so what that means is that we can then use frequency domain analysis to separate the modulating signal from the non-modulating signals. And so because this property is very specific to the NV center, only the nanodiamonds, the nanodiamond fluorescence will have this fixed frequency modulation, whilst the background autofluorescence, which we want to get rid of, will be constant. And so we can use, so in the frequency domain, either by doing a Fourier transform, or we use the lock-in algorithm, but it's basically the same thing. You can separate the modulating signal from the static signal, and in that way you can increase your signal to background ratio, and in turn improve your sensitivity, improve your limit of detection. This is what that looks like. So you can see here the microwave power is the square wave, and then these four traces are actually real data. So the orange is a strong positive, so you can see that when the microwave power is low, the fluorescence is high, and then when the microwave power is high, the fluorescence is low. And you can just use this lock-in algorithm to get the amplitude of this modulating signal. And so that's a strong positive. Then you have a medium positive here in purple, and a weak positive, and then this negative. So this is the strip with no nanodiamonds is just perfectly flat because there's no modulation. And then underneath this is the output of the lock-in algorithm over a range of frequencies, and this is an absolute sinc function, which is the Fourier transform of a square pulse. And this is, I mean, I'm not going to go into detail about all this stuff, but this is just a bit of parameter optimization. So looking at the modulation frequency, the sampling frequency, we found the modulation frequency didn't really matter that much. The sampling frequency, the main thing really is that you want to have the highest possible exposure time, and that just decreases the noise. And then I suppose this is an important one, which is just looking at the number of frames that you need to take, or the length of measurement that you need to take in order to get a stable signal. And so you can see that for all these 5 positive samples, the signal kind of reaches its maximum value very quickly after 1 or 2 seconds. And it's really the negatives where you need a longer measurement to get down to this kind of stable low value that you want. And this is just noise otherwise. So all our measurements we did here, we did for 15 seconds, which is a perfectly reasonable measurement time for a rapid test. So just some more initial stuff was the functionalization. So non-specific binding, as with all nanoparticle-based diagnostics and all lateral flow tests, is really important. And what we saw, we tested a few different nanodiamonds from Adamas, and we found these polyglycerol-coated ones gave the lowest non-specific binding. Sorry. So we used them as the basis for our assay. So we used DSC to functionalize them. It's very flexible. So you can functionalize anything with an amine group. So we bound antibodies and aminated DNA in that way, and validated with FTIR, where you can see these amide bonds after protein functionalization, which are not there before. And then we also verified with DLS, no significant aggregation, and a small but significant increase in the diameter, which is which corresponds to the size of the proteins that were immobilizing on the surface. So there are two different functionalizations here, the FND biotin and the FND antibody. And the reason for that is we tried two different assays, and I'll just explain the rationale for that now. So the first one we did was we wanted to look at the fundamental limit of detection. So we wanted to exclude any assay-specific factors. So the reason for this is that it's often very difficult to compare nanoparticles in different diagnostic tests in the literature, because they're often using different assays, so different binding components and different binding rates. And so it just makes it really difficult to compare just the nanoparticles. So the idea was is that we would use a biotin-avidin interaction, which is a really strong, really fast interaction between a small molecule and biotin and a protein streptavidin. And with the biotin-avidin model, we should have all the particles that flow past the test line binding. So in that way, we can just measure what the smallest number of nanoparticles that we can detect is, and know how many nanoparticles we have, and just be completely independent of any binding rates or assay parameters. So what we did is we functionalized nanodiamonds with BSA biotin. So here the BSA is just acting as a scaffold protein, and there are 4 biotins per BSA, although I've only drawn 3 here. And they bind directly to the streptavidin, which is printed in a line on the test, just as a lateral flow test, but with perfect binding. So it's kind of our perfect idealized assay. And here are some sample images on the top. So you can see a really clear test line here, going up and down. And you can see this really clear kind of modulating signal as well. But what you can also see is that here, for example, in the 70 attomolar image, there's no kind of visible test line in the fluorescence image, but you can still see this really clear modulating signal in the time trace. And then even here, there's this periodic signal still in the 2.8 attomolar, and then in the 110 zeptomolar and the blank, this is just noise. And so these are the results of that. So this is a serial dilution of biotin functionalized nanodiamonds that are run on these streptavidin printed strips and binding and then measured. So this is using the background subtraction with the microwave modulation and the nanodiamonds, and we got a limit of detection of 820 zeptomolar, which we defined as the intersection of the lower 95% confidence interval of this linear fit with the upper 95% confidence interval of the negative control. And then, so using these same samples, but without doing the background removal with microwave modulation, we got 84 attomolar. So that's an extra 100-fold improvement by using this microwave modulation. So 100-fold improvement in detection limit. And then we did the exact same thing with gold nanoparticles for comparison, and we got 81 femtomolar. So just converting to particle numbers, so that's actually just 26 particles in a 50 microliter sample, which was we were really excited about that. So a really low number of nanoparticles compared to gold nanoparticles, where you're looking at about 10 to the 6 to get a measurable signal. So we saw about roughly 10 to the 5-fold improvement over gold nanoparticles. And a bit later on, I'm going to compare that to the improvement that you get from other fluorescent particles. But yeah, it's a really significant improvement, especially when you compare it to the other ways of improving sensitivity. 10 to the 5 is a really big improvement. So obviously this is an idealized assay, and there are other factors which we talked about before that mean that in a real assay we wouldn't get this level of improvement, and those are non-specific binding and the binding rates of the components. So here we have perfect binding rates, and we have no non-specific binding, or it's not relevant, because here the negative control is a true negative with no nanodiamonds, whilst in a real test where you were trying to detect an analyte, you would have the same number of nanodiamonds in every test, and so you would have a certain amount of non-specific binding in the negatives, which would give you a small signal even in the negatives, which increases the level of the blanks, and so reduces your detection limit. So moving to this real assay, what we were aiming for was the detection of HIV RNA. And so the first thing we did was looking at amplicons. So we decided to base this assay on RPA amplicons. So just briefly, RPA is an isothermal nucleic acid amplification method. So it's a way of multiplying the number of any nucleic acid target, and it works almost very similarly to PCR, but just using enzymes instead of temperature to do the various steps. So it's isothermal, and it works optimally, I think, at 37-ish degrees. So it's kind of it's nice that it works at relatively low temperatures and it doesn't require any thermocycling. So what we did is we made a load of amplicons, and then we measured how many amplicons we had, and then did a serial dilution to work out what the smallest number of amplicons we could detect was in this kind of sandwich assay, the one that I showed before. And this is what we found trying with 3 different size nanodiamonds. And we used 600 nanometer, 200 nanometer, and 120 nanometer nanodiamonds. And we found, as we expected, that the largest particles were the best because they have the highest fluorescent signal per particle. Actually, we found that with the biotin-avidin assay as well, although I didn't show that data. Although the improvement is less here, and that's again because of the non-specific binding. But yeah, so we got 3.7 femtomolar, which is in this case a 7,500-fold improvement over gold nanoparticles, and the difference in that improvement factor is about 13-fold, and that corresponds exactly to the difference in the level of the negative control signal. So the negative control in this kind of real assay is 13-fold higher than a true blank with no nanodiamonds, and that is what has, and that corresponds to this decrease in our improvement over gold nanoparticles. Having said that, 7,500-fold is we were really happy with that improvement. So then so then we moved to kind of a more full assay. So in this case, we started off with HIV RNA, and then we actually did this 10-minute isothermal amplification as part of the assay. So we started off with RNA. We did a 10-minute reverse transcription, and so RT-RPA, so where you mix the reverse transcriptase and the RPA together, happens all at the same time in 10 minutes to multiply the copies of nucleic acid, and then using the same nanodiamond binding as before. So we're sort of improving the sensitivity from the bottom and from the top at the same time. So we're improving it from the bottom by multiplying the number of targets that we have, and then improving it from the top by increasing the signal per target. That meant that what we were able to do is get single copy detection with just a 10-minute RPA amplification, and that's really what the nanodiamonds give you, is the ability to detect a small number of amplicons, which means you can amplify for less time and still get really good detection limits, or single copy detection limits in this case. So we then looked at applying to some clinical samples just as proof of concept. We didn't do a full clinical study or anything, but we used a clinical standard from University College London Hospital, which is our kind of adjacent hospital, and got a good signal to blank ratio as we expected. And then we looked at a seroconversion panel. This is kind of so this is where you have a regular blood donor who contracts HIV and then seroconverts. And so they're often used to look at kind of early detection of HIV. And so what we saw is our negatives were pretty good. So this is comparing PCR positive and negatives with our assay, and so what we saw is our negatives are pretty good, and most of our positives were, but we missed this positive, obviously. So yeah, this just requires a lot more work to work out. I mean, so this wasn't a nanoparticle problem or a test problem. This was an amplification problem. So we need to work out kind of why that sample didn't amplify properly. But it's encouraging that we came up as early as PCR, I think. So yeah, as I said earlier, I'm just going to show you a really short comparison with some other fluorescent nanoparticles. that people have used on lateral flow tests. And as I mentioned, it's really hard to compare between papers because everyone uses different assays. So I've limited this to papers that also did amplicon detection in a similar way and also measured the limit of detection with amplicons, not including the amplification step like we did. So there's the range of different nanoparticles used here, from organic fluorophores, European particles, up-converting phosphors that I talked about before, quantum dots, dye-encapsulating liposomes, and then what we did. And yeah, this isn't every particle that's ever been used, but these are the studies that I found that actually detected amplicons so that we could do this direct comparison. And where they also, like us, compared with gold nanoparticles as the gold standard, that's really helpful. And so I've included where they did that, because then there's no kind of approximation because the assay is exactly the same. So where they didn't done that, I've included this improvement factor as well. So this is reported in moles. So we detected of amplicons, we detected 1.9 times 10 to the minus 19 moles with nanodiamonds, and 3 times 10 to the minus 16 moles of with gold nanoparticles. And this is of amplicons. And the next best these up converting phosphors with 3 times 10 to the minus 17 and minus 16. And there's a lot of kind of around the 10 to the minus 15 range. And the ones that reported gold nanoparticles, you've got this 300-fold for European particles and 100-fold for these up-converting phosphors. So we showed a relatively pretty big improvement with the nanodiamonds. So just to summarize, and then move on to a little bit of the future outlook. We use these bright, stable fluorescent particles that give us on their own a really big improvement over gold nanoparticles. Then we got a further 100-fold improvement using this selective modulation, using a low power microwave field. In this idealized biotin-avidin assay, which we think is really good for benchmarking, we showed a 10 to the 5-fold improvement over gold nanoparticles, giving just 26 particles in a 50 microliter sample. Then we detected amplicons with with a limit of detection of 3.7 femtomolar with 600 nanometer particles, which was a 7,500-fold improvement over gold nanoparticles, currently the most widely used. And then we showed that by including a short 10-minute amplification step, we detected single copies of HIV RNA. So now I just wanted to summarize the future outlook for this technology. So the first thing that I really wanted to emphasize is that this is a really flexible system. So our nanodiamond assay is based on these two small molecule modifications, so a digoxygenin and a biotin. And so you can really, you can apply this to loads of different assays and loads of different test formats just by including these two small molecule modifications. So for example, if you wanted to apply to antigen testing, you could make an antibody sandwich and then just modify your two antibodies with digoxygenin and biotin and really not change anything else about the system. Also, it's easily adaptable to different nucleic acid targets by just changing the primers. So that's something that we're really keen to do, is explore all the different options for where nanodiamonds can be applied, what assays and what targets, to really sort of identify where their strengths are and where they can be most beneficial. One thing we're doing at the moment is trying to apply this existing assay to COVID-19, obviously to address the need. And as part of that, we're trying to sort of make the assay, take the assay somewhere which is a bit more amenable to the point of care, so or to low resource settings. So at the moment, there are still some steps in it that need to be done in the lab. So for example, with the clinical sample work, we included an RNA extraction step, which was laboratory based, which obviously you would want to change when bringing this to low resource settings. There's also a purification step in the assay at the moment that we're trying to eliminate the need for. And then finally, the obvious disadvantage of using fluorescent nanoparticles is the need for a fluorescence reader, which you don't have with gold nanoparticles. So at the moment in this work, we've been using a fluorescence microscope. And so what we're working on is kind of miniaturizing that down. And so this is an example of a prototype of a smartphone connected fluorescent lateral flow test reader, which also includes the components that we would need to do the microwave modulation. So yeah, this kind of thing would be important for something like this would be important for applying this in low resource settings. And then we're also looking into further applications, more exploratory work with nanodiamonds and other ways that we can improve sensitivity. One thing I really wanted to highlight was antigen testing. So with hindsight, I think that antigen testing is maybe a better application for the nanodiamonds than nucleic acid testing, and that's because with the amplification based nucleic acid testing, it's really sensitive and fast with a 10-minute amplification step. But what you can do actually is just amplify for longer, get more target, and use a less sensitive label. So what the nanodiamonds give you the ability to do is to be sensitive and fast, but you could amplify for longer and use a less sensitive label. Whilst with antigen testing, your sensitivity improvement just translates directly into the improvement in analytical sensitivity of the test. So for that reason, I think antigen testing is a really exciting path for the nanodiamonds. So for that, we did a proof of concept detecting the HIV capsid protein P24 in a sandwich assay using a VHH nanobody and an antibody functionalized nanodiamond. And just with this quick proof of concept work, we got 120 femtomolar limit of detection. And that's with 120 nanometer particles, so lots of scope for improving that. So I think that's a really exciting direction. I also wanted to draw attention to this work from Diagnostics on using nanodiamonds, fluorescent nanodiamonds. It came out about the same time as our work actually, and using fluorescent nanodiamonds to detect the Ebola virus glycoprotein. And they actually used this axin reader, I think, to detect the Ebola glycoprotein. So finally, I just wanted to thank you all very much for listening, and to show you this picture of our whole. This is, I think, the last time that our whole research consortium was all together. And in the middle there is Professor Rachel McKendry, my PI, who's also the director of the iSense consortium. And yeah, with that, just just put up our website and my email address in case you want to contact me. And just say, and a link to the paper, and just say thank you very much for listening, and I'd be really delighted to answer any questions that you might have. Thank you very much.